mention that if my matrix is upper triangular matrix, lower triangular matrix, or diagonal matrix, we don't need to solve it using the characteristic equation. Directly by sense, the diagonal represent the eigenvalues. It means this is lower triangular matrix, this is the first eigenvalue, the second eigenvalue, the third eigenvalue, as I show here. So in general, let me summarize the discussion here. If A is n by n matrix and lambda is a real number, okay, then lambda could be eigenvalue of A. We can find it by solving lambda I minus A equals 0, which have let me say different numbers for lambda. It could be one value, more than one value, 3 value, 4 value, and so on. Okay, it could be repetitive. Okay, also there is non-vector x. X is non-zero vector. Okay, which represent ax equal lambda x, and we can solve the characteristic equation to find lambda as we mentioned. Finding now, after we finish this, let's go to find eigenvector. Okay, for each eigenvalue there is eigenvector, and putting them together we have eigenspace. Okay, let's have a look here. This is 3 by 3 matrix. 3 by 3 is given to us. Now we say that determinant of A minus lambda I equals 0. We do this. We go through the solution. Here we can see here, after I did the determinant, I solve it here. I got the eigenvalues. I found that I have 4 and I have minus 2 repeated twice. For each one of these eigenvalues, we will have eigenvectors. Let me start first with lambda equal minus 2. Now I will substitute here by minus 2. This lambda will be minus 2, as you can see here. So substitute here minus 2, minus 2, minus 2. We got this matrix. Multiply by x, as we say, equals 0, because we say ax equals 0. Okay, or let me say here lambda I minus a equal x equals 0. Okay, now this row times this column equals 0, as you can see here. 3x1 minus 3x2 equals 0, and this row by this row equals 0. Forget about these because we already include them here, but 0 x3 equals 0. This means that x3 could be any value. I call it s as example. And from this part I will say, okay, let's assume x2 to be any value which is t. Substitute here t and simplify. We'll find that x1 equal minus t, the opposite of x2. Now let me put them. We will say, okay, the eigenvector will be in this way. Okay, x1, x2, x3 will equal 2. x1 we say it is minus t. x2 we say it is t. x3 we say it is s. I put them in this way. Now t here and s here. Let me separate t's from s. I will write t as a common. What is left from here? Minus. What is left from here? Minus 1. And this is supposed to be 0 because no s. While here I will take s. These are zeros and this one will be 1. So this is the eigenvectors in the eigenspace I'm looking for when lambda equal minus 2. We repeat the same discussion for lambda equal 4. Okay, also I substitute here 4, here 4, here 4. I got this matrix by x equals 0. Also I multiply this part by this part. It gives me here the equation. This part by this part it would be 0, which means 6x3 equals 0. x3 supposed to be 0. There is no other value. It have to be 0. You see here? Now the same thing, x2 and x1 we got them. They are equal now. In this example, this part. Now let me substitute. We will say x1, x2, x3 will be t0. Let's take t common. What is left? 1, 1, 0. This is the base for eigenspace of the corresponding lambda equal 4. Also feature here to be mentioned, a square matrix A will be invertible, okay, invertible if and only if lambda is not 0, because if lambda is 0, it will the determinant will be you see here not equal to 0. Okay, if it's not equal to 0, then it means lambda not equal to 0 too. See here as example, when we find determinant of a value which is not equal to 0, then lambda, and lambda is not equal to 0, this means that the eigenvalue of a is invertible. Okay, but if determinant equals 0, lambda equals 0, then there is no invertible for this matrix. Now back to the example I started the eigenvalues with it. Now if we apply this on the characteristic equation here, a minus lambda I for the example, we will find that we have two values for lambda. Lambda could be 1 or 1 over 2. We will find by using the characteristic equation here equals 0, we determine it. Okay, we will find that the lambda will be 1 and 1 over 2. Okay, now multiplying a, by the way, solving for 1, we will go at eigenvector. Okay, and solving for 1 over 2, we will go at this eigenvector. Now if I multiply the eigenvector by the matrix A, we will find it does not change, x1, and the eigenvector here by matrix A, we will go this 1 over 2 at the end. Okay, what this tell me? This tell me rather than I do multiply A here twice to get this matrix, or triple times to get this, or 100 times to get this, I directly can use eigenvalue. I mean, rather than we apply square on the matrix, we will apply square on the eigenvalue. As example, lambda was found to be 1.5. Okay, you see here ax1, the eigenvector for lambda 1, ax2 for lambda 2. When we multiply them, we got this. Okay, why don't we square here and do the calculation by eigenvectors? We don't need to square the matrix. Squaring one number better than squaring matrix with many with larger dimension. This make my task easy, and we will use it. We will use it in solving a set of differential equation later on soon. Now one more example on eigenspace. As you can see here, this is matrix A given to you. Now we want to solve for eigenspace, eigenvalue, eigenvector, eigenspace. Okay, have a look. First of all, I solve the characteristic equation to find lambda. I solve it. I got this equation. I solve the equation. I got lambda 1 and 2. Now for 1, I will go to find eigenvector, and for 2, I going to find eigenvector and eigenspace. Okay, I will put them in this way. This is a minus lambda I, and this is x supposed to be equal to 0 according to the definition. Lambda I minus a equals 0. Okay, you may say, okay, can I put it a minus lambda I equal by x equals 0? Yeah, you can, because it's just multiplying by minus 1. Okay, now let me start with lambda equal to the first eigenvalue. I substitute it here by lambda equal to, and I solve it the same way. I found x1, x2, x3 in terms of st. I put them here. I splitted them here, s's and t's, as you can see here. Then what is left is the eigenvectors I'm looking for. These are the two eigenvectors for lambda equal 2. I repeat the same discussion for lambda equal 1. Also I substituted. I got this is the matrix, this is x and this is 0. I solve it in terms of s and t's. I found that they can be solved only by s, no need for t's here, and I got one eigenvector, as you can see here, for this one. Now after this discussion, what I want you to do, please try to solve eigenvalue, eigenvector for this matrix. I will stop here to continue in the next session.